What if every moment in history, from the birth of stars to the rise of civilizations, could suddenly rewind? What if the universe itself hit the brakes on its expansion, collapsing back into a single, unimaginable point? This isn't science fiction, it's the Big Crunch, a theory that flips our understanding of the cosmos on its head. Today, we're diving into one of the most profound questions in science. What happens if the universe reverses? From the fate of galaxies to the possibility of a cosmic rebirth, this journey will challenge everything you think you know about time, space, and reality itself. By the end of this video, you'll not only understand the science behind the Big Crunch, but also why it could change the way we see the universe and our place within it. So, let's take a closer look at what it means for the cosmos to rewrite its own story. Picture this: the universe, vast and ever-expanding, suddenly begins to slow down, then stops, and finally starts collapsing in on itself. This is the Big Crunch, a fascinating and somewhat eerie theory about how our cosmos might meet its end. Unlike the Big Bang, which describes the universe's explosive birth, the Big Crunch suggests a dramatic reversal, a cosmic contraction where everything is pulled back together. But what forces could cause such a reversal? At the heart of this idea is gravity, the same force that keeps your feet on the ground. Gravity, pulling matter together, could eventually overcome the universe's expansion, especially if the density of matter is high enough. Imagine galaxies, stars, and even light itself being drawn inward, as if the universe were taking a deep breath after its long exhale. But there's a twist. Dark energy, the mysterious force driving the universe's accelerated expansion, could play a critical role in determining whether this collapse happens. If dark energy weakens over time, gravity might gain the upper hand, setting the stage for the Big Crunch. What's intriguing is how this scenario contrasts with the Big Bang. While the Big Bang marks the beginning of fiery expansion from an unimaginably dense state, the Big Crunch could represent the end, a return to that same density. It's almost poetic, isn't it? A universe that begins with a bang might end with a crunch. But this isn't just a theoretical curiosity, it's a question that challenges our understanding of the cosmos. What would it mean for time, space, and the very fabric of existence if the universe were to collapse? By exploring the Big Crunch, we're not just looking at a potential cosmic endpoint, we're peering into the delicate balance of forces that shape the universe. Gravity pulling inward, dark energy pushing outward, it's a cosmic tug-of-war that could determine the ultimate fate of everything we know. And as we dive deeper into this theory, one thing becomes clear: the universe is full of surprises, and its story is far from over. But what if the force driving the universe's expansion suddenly changed its tune? Enter dark energy, the enigmatic power behind the universe's accelerating growth. This mysterious force isn't just shaping the cosmos as we know it. It could also hold the key to whether the universe collapses back on itself in a Big Crunch. The fate of everything, galaxies, stars, even time itself, may hinge on how dark energy behaves in the distant future. Right now, dark energy seems to be winning the cosmic tug-of-war, pushing galaxies apart faster and faster. But scientists aren't entirely sure if this will always be the case. Imagine dark energy as a dimmer switch. It could stay constant, grow stronger, or even weaken over time. If it weakens, the universe's expansion might slow down and eventually reverse, setting the stage for a dramatic collapse. On the other hand, if it strengthens, the universe could stretch endlessly into a cold, dark void. And if it stays the same, well, that's where things get even more uncertain. This uncertainty has sparked heated debates among cosmologists. Some argue that dark energy's strength is fixed, governed by a constant known as the cosmological constant. Others propose that dark energy is dynamic, changing over time in ways we don't yet understand. These competing ideas aren't just academic. They're crucial for predicting whether a Big Crunch is even possible. After all, if dark energy behaves unpredictably, the universe's fate could be far stranger than we've ever imagined. What makes this even more fascinating is that we're still in the dark, literally, about what dark energy actually is. Is it a property of space itself, a new kind of field, or something entirely beyond our current understanding? Until we solve this puzzle, the question of whether the universe will collapse remains wide open. And that's what makes cosmology so thrilling. It's a field where every discovery could rewrite the story of everything. What if the universe's ultimate fate isn't a fiery collapse but a slow, icy fade into oblivion? As we dive deeper into the mysteries of the cosmos, we're faced with two compelling yet opposing theories, the Big Crunch and the Big Freeze. These ideas don't just paint different pictures of the universe's end. They shape how we understand its very nature. Let's break them down and explore what makes each theory unique and why scientists are still debating which one might hold the truth. The Big Crunch, as we've touched on earlier, suggests that the universe will eventually stop expanding and begin to collapse in on itself. Picture this: all the galaxies, stars, and planets being pulled back together into an unimaginably dense point, almost like hitting rewind on the Big Bang. This scenario hinges on the idea that the universe has enough matter and gravity to overcome the force of dark energy, which currently drives its expansion. If gravity wins out, the cosmos could end in a spectacular cosmic crunch. But then there's the Big Freeze, a theory that paints a very different picture. Instead of collapsing, the universe could continue expanding forever, growing colder, darker, and emptier as it stretches into infinity. In this scenario, dark energy dominates, pushing galaxies farther apart until they're so distant that no light from one can ever reach another. Stars would burn out, black holes would evaporate, and the universe would fade into a state of cold, lifeless stillness. It's a haunting vision of an endless, frozen void. So, what determines which of these fates awaits us? It all comes down to a few critical factors. First, there's the role of dark energy, a mysterious force that makes up about 68% of the universe's energy. If dark energy remains constant or weakens over time, gravity could eventually take over, leading to the Big Crunch. But if dark energy grows stronger, it could keep pushing the universe apart, sealing its fate as a frozen expanse. Then there's the matter of the universe's density. If the cosmos contains enough matter, its gravitational pull could counteract the expansion and trigger a collapse. But if the density is too low, the universe will keep stretching out indefinitely. Finally, the curvature of space-time plays a role too. A closed universe, shaped like a sphere, could collapse back in on itself, while an open or flat universe would likely continue expanding forever. The debate between these two theories isn't just academic. It's a window into the fundamental forces that govern our reality. And while we don't yet have all the answers, ongoing observations of distant supernova, the cosmic microwave background, and the large-scale structure of the universe are helping scientists piece together the puzzle. Each new discovery brings us closer to understanding whether the universe is destined for a fiery end or a cold, silent fade. To grasp the idea of a reversing universe, we need to take a closer look at the fundamental forces and laws that govern our cosmos. At the heart of this discussion are three pillars of modern physics: thermodynamics, general relativity, and quantum mechanics. Together, they paint a picture of how the universe might one day stop expanding and begin collapsing back in on itself. Let's start with thermodynamics, specifically the concept of entropy. Entropy is essentially a measure of disorder in a system. In our universe, entropy tends to increase over time, meaning things naturally move toward chaos. But in a reversing universe, this trend could flip. If the universe were to contract, entropy might decrease, leading to a state of increasing order, a dramatic shift from the chaos we see around us today. Next, we turn to general relativity, Einstein's groundbreaking theory that describes how gravity shapes space and time. In a collapsing universe, gravity would become the dominant force, pulling galaxies, stars, and even light back toward a central point. This process, known as gravitational collapse, could eventually lead to a singularity, a point of infinite density. It's like rewinding the Big Bang, but instead of an explosion, we'd see everything rushing inward, compressing into a single, unimaginably dense spot. Then there's the curious role of quantum mechanics. At the smallest scales, particles don't always behave as we'd expect. Quantum fluctuations, tiny, random changes in energy, could influence how a reversing universe unfolds. Some theories even suggest that time itself might reverse in such a scenario. Imagine a universe where cause and effect flip, where the future influences the past. While this sounds like science fiction, it's a possibility rooted in the strange, counterintuitive world of quantum physics. By combining these ideas, entropy, gravity, and quantum mechanics, we start to see how a big crunch might occur. It's not just a simple collapse, it's a complex interplay of forces and laws that could reshape the very fabric of reality. And while the concept of a reversing universe is still theoretical, it offers a fascinating glimpse into the potential fate of everything we know. So, let's dive into the timeline of a big crunch. When could this cosmic reversal actually happen? If the universe were destined to collapse back in on itself, how long would it take to go from the expansion we see today to that final, dramatic collapse? The answer isn't straightforward, but current cosmological models give us some intriguing possibilities to explore. Right now, the universe is expanding, and galaxies are moving away from each other at an accelerating rate, driven by dark energy. But if this expansion were to slow down and eventually reverse, it could set the stage for a big crunch. Scientists estimate that this entire process, from the slowing of expansion to the ultimate collapse, could take tens of billions of years. To put that into perspective, our universe is currently around 13.8 billion years old, so we're talking about a timescale that dwarfs the entire history of existence as we know it. But what factors could influence this timeline? One key element is the density of the universe. If there's enough matter and energy to overcome the force of dark energy, gravity could gradually pull everything back together. Some models suggest that if the density of the universe is just slightly higher than what we currently observe, the collapse could happen sooner, perhaps within 100 billion years or so. On the other hand, if dark energy continues to dominate, the timeline could stretch even further, pushing the big crunch into the realm of trillions of years. Another factor to consider is the role of black holes. As the universe contracts, black holes could merge, growing larger and more powerful. These cosmic giants would accelerate the collapse by pulling in more matter and energy, creating a kind of feedback loop that speeds up the process. And as the universe nears its final moments, temperatures would skyrocket, galaxies would collide, and space itself would become denser and more chaotic. It's a fascinating, if somewhat unsettling, glimpse into the distant future. But here's the thing, this is all based on hypothetical scenarios. The truth is, we don't yet know the ultimate fate of the universe. The Big Crunch is just one possibility, and it hinges on conditions that could change as we learn more about dark energy, dark matter, and the fundamental forces shaping our cosmos. For now, the timeline remains a tantalizing mystery, a reminder of how much we still have to discover about the universe and its incredible story. As the universe begins its hypothetical reversal, the fate of galaxies becomes one of the most captivating and dramatic aspects of this cosmic scenario. Picture the vast expanse of space, once expanding at an accelerating rate, now slowly turning inward. Galaxies, those colossal islands of stars, gas, and dark matter, would no longer drift apart, but instead begin to move closer together. Over eons, the distances between them would shrink, setting the stage for a series of extraordinary events. First, galactic collisions would become inevitable. In an expanding universe, galaxies like our Milky Way and Andromeda are on a collision course, but in a collapsing cosmos, such encounters would happen far more frequently. Imagine entire galaxies, each containing billions of stars, slamming into one another with unimaginable force. These collisions would trigger bursts of star formation as gas clouds compress, igniting new stellar nurseries. But this fiery rebirth would be short-lived, as the universe's reversal would eventually lead to a scarcity of resources needed to sustain such processes. As galaxies merge, their stars would face a grim fate. In the early stages of the collapse, stars might continue to burn brightly, but over time, the lack of new material to form stars would lead to a slow dimming of the cosmos. Eventually, stars would exhaust their fuel, leaving behind remnants like white dwarfs, neutron stars, and black holes. The universe, once teeming with light, would grow darker and colder. Black holes, already mysterious and powerful, would play an even more dominant role in this collapsing universe. As galaxies merge, their central supermassive black holes would collide, creating even larger behemoths. These monstrous entities would devour nearby stars and gas, growing to unimaginable sizes. Over time, the universe could become a patchwork of these supermassive structures, with black holes acting as the anchors of a shrinking cosmos. The formation of these supermassive black hole clusters would mark a turning point. Instead of galaxies being the primary structures of the universe, black holes would take center stage, reshaping the fabric of space-time itself. The once vibrant tapestry of stars and galaxies would be replaced by a stark, dark landscape dominated by gravity's ultimate triumph. Yet even in this collapsing universe, there's a strange beauty to contemplate. The interplay of forces, gravity pulling everything inward, black holes merging, and the remnants of stars scattered across the cosmos paints a picture of both destruction and transformation. It's a reminder of the universe's ever-changing nature, even in its final stages. So, as we ponder the fate of galaxies in a collapsing universe, we're left with a profound sense of awe. The cosmos, whether expanding or contracting, remains a place of endless wonder and mystery, where even its end holds the potential for new and extraordinary phenomena. Picture this: a universe no longer expanding, but instead collapsing inward, its very fabric tightening like a cosmic noose. In such a scenario, the stars that once lit up the cosmos would face a dramatic and inevitable transformation. Stars, those brilliant engines of light and energy, are powered by nuclear fusion in their cores. But as the universe contracts, the conditions for their survival begin to unravel. First, consider the fate of stars like our Sun. In a contracting universe, the gravitational forces pulling everything inward would grow stronger, compressing matter at an accelerating rate. Stars would burn through their fuel much faster, their lifespans drastically shortened. For smaller stars, this could mean a quiet but certain demise, burning out and cooling into dim, lifeless remnants. But for more massive stars, the end would be far more spectacular. As these giants exhaust their fuel, their cores would collapse under their own gravity, triggering cataclysmic supernova explosions. These violent events would scatter heavy elements across the universe, seeding the cosmos with the building blocks for new stars and planets, at least for a time. But even this cycle of creation and destruction wouldn't last forever. As the universe continues to collapse, the conditions for new star formation would become increasingly rare. Yet, there's an intriguing possibility here. In the early stages of the Big Crunch, before the universe becomes too dense and chaotic, pockets of gas and dust might still come together to form new stars. These stars, however, would be born into a universe on borrowed time, destined to burn brightly but briefly before meeting their own inevitable ends. And then there's the ultimate fate of the most massive stars, black holes. As the universe contracts, the gravitational pull would grow so intense that even light couldn't escape. Stars that might have once collapsed into neutron stars or black holes under normal circumstances would now face an even more extreme environment. The formation of black holes would accelerate, and these cosmic vacuum cleaners would begin to devour everything in their path, including other stars, planets, and even light itself. In the end, The stars that once defined the universe would fade into darkness, their light extinguished as the universe tightens its grip. But this isn't just a story of destruction, it's a reminder of the delicate balance that allows stars to shine in the first place. And as we ponder their fate, we're left with a profound question. What happens when the very forces that gave birth to the stars become the forces that destroy them? As the universe begins its hypothetical collapse, black holes, those mysterious all-consuming giants, could rise to become the ultimate rulers of the cosmos. Picture this. In a contracting universe, gravity tightens its grip, pulling galaxies, stars, and even light itself into an ever-shrinking space. Black holes, already known for their insatiable appetites, would thrive in this environment. They'd grow larger and more powerful, merging with one another in cataclysmic events that shake the fabric of spacetime itself. Over time, they could devour entire galaxies, swallowing stars, planets, and even other black holes. But what happens when these cosmic titans dominate the universe? The answer lies in something called a Big Crunch singularity. Unlike the Big Bang singularity, where everything exploded outward from an infinitely dense point, a Big Crunch singularity would be the opposite, a moment where all matter and energy in the universe collapses inward, converging into a single, unimaginably dense point. Black holes, having consumed nearly everything, would likely be the last remaining structures before this final collapse. This raises an intriguing question. How would such a singularity differ from the one that birthed our universe? During the Big Bang, the universe expanded rapidly, creating the conditions for stars, galaxies, and ultimately life. A Big Crunch singularity, on the other hand, would mark the end of expansion and the beginning of contraction. It's a cosmic full stop, a moment where the universe's story, at least as we know it, comes to a close. And yet, even as black holes dominate and the universe contracts, there's a strange beauty to this scenario. It's a reminder of the universe's cyclical nature, where endings can also hint at new beginnings. Could a Big Crunch singularity give rise to another Big Bang? Or would it be the final chapter in the universe's grand narrative? These are questions that challenge our understanding of time, space, and existence itself. For now, black holes remain as enigmatic as ever, and the idea of a Big Crunch is just one of many possibilities. But it's a thought-provoking one, inviting us to ponder the ultimate fate of everything we know, and the role these cosmic giants might play in shaping it. What if the fate of the universe isn't just a cosmic tug of war between gravity and expansion? What if the tiniest particles, governed by the strange rules of quantum mechanics, could hold the key to how it all ends, or begins again? When we zoom into the quantum scale, the universe behaves in ways that defy our everyday intuition. Particles pop in and out of existence, energy fluctuates unpredictably, and the very fabric of reality seems to shimmer with uncertainty. These quantum fluctuations, though tiny, could play a massive role in the story of the Big Crunch. At the quantum level, particles don't follow the same rules as the planets and stars we're used to observing. Instead, they behave more like waves, existing in a state of probability until they're measured or interact with something else. This unpredictability means that even in a universe collapsing under its own gravity, quantum effects could introduce wildcard variables. Imagine a cosmic game of Jenga where the blocks are particles and the rules keep changing. Quantum mechanics might pull out a block that no one saw coming, altering the entire structure of the collapse. One of the most intriguing ideas here is how quantum gravity, a theory that attempts to merge quantum mechanics with Einstein's general relativity, could reshape our understanding of the Big Crunch. In our current framework, gravity dominates on large scales, pulling everything together, but at the quantum scale, gravity is almost like a whisper, barely noticeable compared to the other forces. If we could find a way to reconcile these two worlds, it might reveal how quantum effects could either accelerate or disrupt the collapse. Some theories suggest that quantum gravity could create microscopic wormholes, tiny ripples in spacetime, or even new dimensions, each of which could throw a wrench into the machinery of a collapsing universe. And then there's the question of what happens to matter itself during a big crunch. As the universe contracts, particles are squeezed closer and closer together. Under normal circumstances, this would lead to unimaginable heat and pressure, but quantum mechanics could introduce strange new states of matter. Particles might behave in ways we've never seen before, forming exotic structures or even triggering new phases of existence. It's like compressing a sponge, but instead of water, what comes out might be something entirely unexpected. So, while the big crunch might seem like a straightforward collapse, quantum mechanics reminds us that the universe is anything but predictable. It's a realm where the rules we thought we knew might not apply, and where even the smallest fluctuations could have universe-altering consequences. This interplay between the quantum and the cosmic opens up a whole new frontier of possibilities, challenging us to rethink what we thought we understood about the end, and perhaps the rebirth of everything. What if time itself could reverse? As the universe collapses into a big crunch, could the flow of time flip, running backward like a rewinding film? This isn't just a sci-fi fantasy, it's a question that physicists and philosophers have wrestled with for decades. The concept of time reversal is one of the most mind-bending ideas tied to the big crunch, and it challenges everything we think we know about cause and effect, memory, and the very nature of existence. At the heart of this idea is the arrow of time, the one-way flow from past to future that we experience every day. It's why we remember yesterday but not tomorrow, why a shattered glass doesn't reassemble itself, and why we age in one direction. But what if this arrow isn't as fixed as it seems? In a collapsing universe, some theories suggest that the arrow of time could reverse, meaning events might unfold in reverse order. Instead of moving forward, time could flow backward, rewinding the cosmic timeline. But how would this even work? Physicists point to the laws of thermodynamics, which govern the flow of energy and entropy, the measure of disorder in the universe. In our current universe, entropy increases over time, creating the arrow of time we're familiar with. But in a big crunch scenario, as the universe contracts, entropy might decrease. This reversal could theoretically flip the arrow of time, causing time to run backward. It's a wild idea, but it's rooted in the same equations that describe the expansion of our universe today. Philosophers, on the other hand, raise questions about what this would mean for causality, the relationship between cause and effect. If time were to reverse, would causes come after their effects? Would we remember the future instead of the past? These questions push the boundaries of human understanding, blending physics with deep existential inquiry. Some even argue that a reversed arrow of time might not feel any different to us. Our perception of time might simply adapt to the new flow, making backward time just as normal as forward time. And let's not forget the implications for memory. If time were to reverse, would our memories still work the same way? Would we recall events that haven't happened yet? Or would our brains rewire themselves to align with the new direction of time? These are the kinds of questions that make the concept of time reversal so fascinating and so difficult to pin down. While we may not have definitive answers, exploring these ideas helps us appreciate just how strange and mysterious the universe could become in its final moments. So, what if the big crunch isn't the end of everything but just one chapter in a much larger story? Imagine the universe as part of an infinite loop, where every collapse leads to a new beginning. This is where the big crunch meets the fascinating idea of the multiverse. Could our universe be just one of many, each cycling through its own big bangs and big crunches? Some scientists speculate that such a scenario might explain why our universe seems so finely tuned for life. If countless universes exist, each with its own set of physical laws, it's possible that ours is simply one where the conditions allowed stars, planets, and ultimately us to exist. But how could this work? Picture a cosmic dance where universes expand, contract, and then burst into existence again. In this cyclical model, the Big Crunch wouldn't be a final, irreversible event. Instead, it could act as a reset button, compressing all matter and energy back into a singularity, only to trigger another Big Bang. This idea isn't entirely new. It echoes ancient philosophical concepts of eternal recurrence, but with a modern scientific twist. Now, let's dig into the evidence or lack thereof. One of the biggest challenges with this theory is that it's incredibly hard to test. If our universe is just one in an endless cycle, how could we ever observe what lies beyond it? Some researchers point to subtle clues in the cosmic microwave background, the faint afterglow of the Big Bang, as potential evidence of previous cycles. Others argue that the laws of physics as we know them might break down during a Big Crunch, making it impossible to predict what comes next. And then there's the question of entropy, the measure of disorder in the universe. If entropy always increases, as the second law of thermodynamics suggests, how could the universe reset itself without violating this fundamental principle? Some theories propose that entropy might somehow reset during the transition from a Big Crunch to a new Big Bang, but this remains speculative. The implications of a cyclical multiverse are mind-bending. It would mean that reality is far more vast and interconnected than we ever imagined. It would also challenge our understanding of time itself. Instead of a linear progression from past to future, time might loop back on itself, with each cycle of the universe rewriting its own history. So, is this just a wild idea, or could it hold some truth? While the evidence is far from conclusive, the possibility of a multiverse cycle invites us to rethink the very nature of existence. It's a reminder that the universe is full of mysteries waiting to be unraveled, and that sometimes the most profound questions don't have easy answers. Now, let's turn our attention to one of the universe's greatest mysteries, dark matter. This invisible, elusive substance makes up roughly 85% of the universe's total mass, yet it doesn't interact with light or ordinary matter in any way we can directly observe. But just because we can't see it doesn't mean it's not there, or that it's not incredibly important. In fact, dark matter could be one of the deciding factors in whether the universe ultimately collapses into a Big Crunch. Imagine the cosmos as a vast, interconnected web. Galaxies and galaxy clusters are like knots in that web, held together by the gravitational pull of dark matter. Without it, these colossal structures would simply fly apart, unable to maintain their shape. But dark matter doesn't just hold things together, it also influences how the universe expands or contracts. If the universe were to reverse its expansion and begin collapsing, dark matter's gravitational influence would play a critical role in pulling everything back together. The way dark matter is distributed across the cosmos could determine how quickly and how violently a Big Crunch might unfold. If dark matter is clumped unevenly, with dense regions pulling more strongly than others, the collapse might happen in waves, with some areas of the universe falling inward faster than the rest. On the other hand, if dark matter is spread more uniformly, the collapse could be slower and more even, like a cosmic sigh rather than a dramatic implosion. And then there's the question of how dark matter interacts with itself. Scientists are still trying to figure out whether dark matter particles can collide, merge, or even decay over time. These behaviors could subtly alter the timeline of a Big Crunch, either speeding it up or slowing it down. For instance, if dark matter particles interact weakly, their gravitational pull might remain steady over billions of years, steadily drawing the universe back together. But if they interact more strongly, they could create pockets of resistance, delaying the collapse in certain regions. What's fascinating is that dark matter doesn't just shape the universe on a grand scale, it also affects individual galaxies. As the universe contracts, dark matter would pull galaxies closer together, potentially triggering collisions and mergers on an unprecedented scale. Imagine entire galaxies, each containing billions of stars, smashing into one another as they're drawn toward a central point. The resulting chaos would reshape the cosmos, blending stars, gas, and dark matter into a swirling, chaotic mix. So, while dark matter is invisible to us, its influence is anything but. It's the unseen architect of the universe's structure, and if the Big Crunch scenario comes to pass, it will be the force that guides the cosmos back to its beginning. The more we learn about dark matter, the better we can understand not just the fate of the universe, but also the intricate dance of gravity, matter, and energy that has shaped it from the start. So, we've been exploring the idea of the Big Crunch, a universe collapsing back in on itself, reversing the expansion we see today. But here's where things get really fascinating. What about the heat death of the universe? It's a concept that feels almost like the opposite of the Big Crunch. Heat death suggests a universe that keeps expanding forever, cooling down until it reaches a state of maximum entropy, where no energy is left to do any work. It's a cold, dark, and lifeless end. So, how do these two ideas, Big Crunch and heat death, fit together? Or do they? Let's start with heat death. In this scenario, the universe keeps stretching out, galaxies drifting farther and farther apart until stars burn out, black holes evaporate, and everything just fades into a uniform, lukewarm haze. It's the ultimate fate of a universe ruled by entropy, where energy becomes so spread out that nothing interesting can happen anymore. No stars, no planets, no life, just a cosmic stillness. Now compare that to the Big Crunch. Instead of stretching forever, the universe stops expanding, reverses course, and collapses back in on itself. It's not a quiet fade out, it's a dramatic, fiery finale. Galaxies crash together, temperatures skyrocket, and everything gets compressed into an unimaginably dense point. It's the opposite of heat death, a universe that ends with a bang, not a whimper. But here's the paradox. Can these two ideas coexist? Could a universe that's collapsing under its own gravity still experience heat death? The answer lies in the laws of thermodynamics, particularly entropy. Entropy is a measure of disorder, and in a closed system like the universe, it tends to increase over time. In heat death, entropy reaches its maximum because energy is evenly distributed. But in a Big Crunch, entropy might actually decrease as everything gets compressed back into a single point. That's a problem because, according to thermodynamics, entropy can't just go backward without some external influence. So, what's going on? Some scientists suggest that maybe the Big Crunch wouldn't reverse entropy after all. Instead, the collapse could create such extreme conditions like temperatures and densities we can't even imagine. That entropy keeps increasing even as the universe shrinks. It's like squeezing a sponge. The tighter you squeeze, the more energy gets concentrated and the more chaotic things become. In this view, the Big Crunch and heat death might not be so different after all. Both could be paths to maximum entropy, just through different means. But here's another twist. What if the Big Crunch isn't the end? Some theories propose that a collapsing universe could rebound, leading to a new Big Bang and a fresh cycle of expansion. If that's the case, then entropy might reset, and the story of the universe becomes a never-ending loop of expansion, collapse, and rebirth. It's a mind-bending idea, but it raises even more questions about how entropy behaves in these extreme conditions. So, while heat death and the Big Crunch seem like opposites at first glance, they might actually be two sides of the same cosmic coin. Both are governed by the same fundamental laws, but they play out in wildly different ways. Whether the universe ends in a cold, quiet fade or a fiery collapse, one thing's for sure: the story of entropy is at the heart of it all. And as we try to unravel these mysteries, we're reminded just how strange and beautiful the cosmos can be. The cosmic microwave background, or CMB, is like a time capsule from the universe's infancy, a faint glow of radiation left over from the Big Bang. It's the oldest light we can observe, and it gives us a detailed picture of what the cosmos looked like when it was just a baby, only 380,000 years old. But what if the universe weren't expanding anymore? What if instead it started collapsing toward a big crunch? How would the CMB change, and what could it tell us about this cosmic reversal? In an expanding universe, the CMB has been cooling and stretching over billions of years, its wavelengths growing longer as space itself stretches. This is why we detect it today as microwave radiation, a faint echo of the universe's fiery beginnings. But in a collapsing universe, the story would be very different. As galaxies, stars, and even space itself began to contract, the CMB would start to heat up. The wavelengths of this ancient light would shorten, shifting from microwaves toward higher energy forms of radiation, like infrared or even visible light. It would be as if the universe were rewinding, turning up the heat on its oldest relic. But the CMB wouldn't just change in temperature, it would also change in structure. The tiny fluctuations we see in the CMB today, the faint ripples that map the early universe's density variations, would begin to evolve in unexpected ways. In a collapsing universe, gravity would take over, amplifying these fluctuations as matter clumps together. Regions that were once slightly denser than their surroundings would grow denser still, pulling in more and more material. Over time, this could lead to a dramatic reshaping of the CMB's patterns, as the universe's structure becomes increasingly distorted by the pull of gravity. And then there's the question of time. In a collapsing universe, time itself might behave differently. As the cosmos contracts, the rate of change could accelerate, compressing billions of years of cosmic evolution into a much shorter span. The CMB, which now stretches across the sky in a relatively uniform glow, might become patchy and uneven, reflecting the rapid changes happening all around us. It's a strange thought. The very fabric of the universe, as seen through its oldest light, would begin to unravel. What's fascinating is that these changes wouldn't happen all at once. The CMB would serve as a kind of cosmic barometer, giving us real-time updates on the universe's collapse. As the temperature rises and the patterns shift, we'd have a front-row seat to the universe's final act, a chance to witness the big crunch as it unfolds. It's a sobering reminder of how interconnected everything is, from the smallest fluctuations in the early universe to the fate of the cosmos itself. Imagine a universe that's not expanding but collapsing inward, pulling everything: galaxies, stars, planets, and even the atoms in your body, toward a single inescapable point. This is the Big Crunch, a cosmic reversal of the Big Bang. But here's a chilling question: could life as we know it survive in such a collapsing universe? The answer, unfortunately, is almost certainly no. As the universe contracts, the conditions for life would deteriorate rapidly, and the very fabric of reality would begin to unravel. Let's explore why. First, consider the temperature. In a contracting universe, the energy from all those collapsing stars and galaxies would be compressed into an increasingly smaller space. The result? A universe that grows hotter and hotter, eventually reaching temperatures so extreme that no known form of life could endure. Even the hardiest extremophiles on Earth, organisms that thrive in boiling water or freezing cold, would stand no chance. The heat would vaporize everything, from planets to the molecules that make up living cells. But the heat is only the beginning. As the universe contracts, the forces that hold atoms together would begin to falter. In the final stages of the Big Crunch, the intense gravitational pull would overcome even the strongest atomic bonds. Protons and neutrons, the building blocks of matter, would break apart, reducing everything to a chaotic soup of fundamental particles. Life, as we understand it, relies on the stability of atoms and molecules to function. Without that stability, the chemistry of life becomes impossible. And then there's the philosophical side of it. If the universe were to collapse, it wouldn't just mean the end of life, it would mean the end of everything. No galaxies, no stars, no planets, no memories of what once was. It's a thought that forces us to confront the fragility of existence. We often think of the universe as eternal and unchanging, but the Big Crunch reminds us that even the cosmos has a beginning and perhaps an end. What does that mean for our understanding of life, purpose, and the legacy of humanity? Some might argue that life in some form could find a way to adapt. After all, life on Earth has proven remarkably resilient, evolving to survive in environments once thought uninhabitable. But the Big Crunch presents challenges beyond anything life has ever faced. It's not just a change in environment, it's the destruction of the very rules that make life possible. In the face of such overwhelming odds, the idea of survival seems almost laughable. Yet, even as we grapple with the grim reality of the Big Crunch, there's something strangely inspiring about it. It forces us to appreciate the fleeting beauty of the universe we inhabit, to cherish the time we have, and to ponder our place in the grand scheme of things. Whether or not the Big Crunch ever happens, the very thought of it invites us to reflect on what it means to exist in a universe that's both vast and fragile, eternal and impermanent. And perhaps in that reflection, we find a deeper understanding of what it means to be alive. As the universe collapses inward, the very fabric of space-time begins to unravel in ways that defy our current understanding of reality. Picture this: the dimensions we rely on to navigate our world, length, width, height, and even time, start to distort and compress. The once expansive universe, with its galaxies drifting apart, now begins to fold in on itself, pulling everything closer together. But what happens to space-time itself during this process? Could it warp, twist, or even tear apart entirely? One of the most fascinating aspects of this scenario is how gravity, the force that governs the motion of planets and stars, would intensify as the universe contracts. In a Big Crunch, gravity would no longer be just a background player. It would become the dominant force, driving everything toward a single point. This extreme gravitational pull could cause space-time to curve so dramatically that the familiar rules of physics we rely on today might no longer apply. Imagine a cosmic rubber sheet stretched thin over the vastness of the universe, suddenly crumpling into a dense, chaotic knot. That's the kind of distortion we might expect as the universe collapses. But it doesn't stop there. As space-time warps under the pressure of the Big Crunch, the very nature of reality could shift. Some theories suggest that the fabric of space-time might develop rips or tears, creating regions where the laws of physics break down entirely. These so-called singularities could act as gateways to entirely new realms of existence. Or perhaps they'd simply mark the end of everything we know. The implications are staggering, raising questions about whether the universe could ever recover from such a collapse, or if this would truly be the end of time itself. What's even more intriguing is how this process might challenge our understanding of causality, the idea that cause precedes effect. In a collapsing universe where time itself is compressed and distorted, the sequence of events could become scrambled. Past, present, and future might blur together, creating a reality where the concept of before and after loses all meaning. It's a mind-bending scenario that forces us to rethink not just how the universe works, but how we perceive our place within it. And yet, amidst all this chaos, there's a strange beauty to the idea of the Big Crunch. It's a reminder that the universe, for all its vastness and complexity, is not immune to change. The same forces that brought galaxies into existence could one day pull them back together, reshaping the very fabric of reality in the process. It's a humbling thought, one that invites us to consider the impermanence of everything we know, and to marvel at the extraordinary possibilities that lie beyond the limits of our current understanding. As the universe contracts toward a Big Crunch, the behavior of light would become one of the most fascinating and bizarre phenomena to witness. Light, which we often take for granted as a constant in our lives, would face extraordinary challenges in a collapsing cosmos. To understand this, let's start with the concept of redshift, a phenomenon we're already familiar with in our expanding universe. In an expanding universe, light from distant galaxies stretches, shifting toward the red end of the spectrum. But in a contracting universe, the opposite would happen. Light would undergo blueshift, compressing as the universe shrinks, causing wavelengths to shorten and shift toward the blue end of the spectrum. This would make distant objects appear brighter and more energetic, but it's only the beginning of the strange effects on light. As the collapse accelerates, space itself would become denser and more crowded. Imagine trying to shine a flashlight in a room that's shrinking faster and faster. The walls would close in, and the light would have less room to travel. In a collapsing universe, light would face a similar fate. Photons, the particles of light, would find their paths increasingly constrained, unable to travel freely as they do now. Over time, even the light from nearby stars and galaxies would struggle to reach us, trapped in the tightening fabric of space. But the most dramatic fate for light would come as the universe approaches the singularity, the final moment of the Big Crunch. Here, gravity would become so overwhelming that even light, the fastest thing in the universe, couldn't escape. It would be pulled inward, trapped in the gravitational well of the singularity, leaving the cosmos in darkness. This final collapse would mark the end of light as we know it, a cosmic curtain call where even the faintest glimmer would vanish into the abyss. What's truly mind-bending is that this process wouldn't just affect visible light. All forms of electromagnetic radiation, radio waves, X-rays, even gamma rays would face the same fate. The universe, once filled with the glow of stars and the hum of cosmic radiation, would grow silent and dark, a stark contrast to the vibrant expanse we see today. It's a chilling thought, but one that highlights just how profoundly the fate of light is tied to the destiny of the universe itself. And yet, even in this collapsing scenario, light plays a crucial role in helping us understand the universe's final moments. By studying how light behaves under extreme gravitational forces, scientists can piece together the physics of a collapsing cosmos, offering clues about the ultimate fate of everything we know. It's a reminder that light isn't just something we see. It's a messenger carrying the story of the universe across unimaginable distances and through the most extreme conditions imaginable. As the universe begins its descent into a big crunch, the fate of planets like Earth becomes a haunting question. Picture the vast tapestry of planetary systems, each orbiting stars that have burned brightly for billions of years. In a collapsing universe, these celestial bodies would face forces beyond comprehension, forces that would unravel the very fabric of their existence. First, as the universe contracts, the gravitational pull between objects would intensify exponentially. Planets, once held in stable orbits by the delicate balance of gravity and momentum, would find themselves pulled closer and closer to their stars. Over time, this relentless tug-of-war could destabilize entire solar systems, sending planets spiraling out of control. Some might collide with their stars in cataclysmic impacts, while others could be flung into the cold void of space, untethered from their gravitational anchors. But the destruction doesn't stop there. As space-time itself begins to collapse, the density of matter in the universe would skyrocket. Black holes, already lurking in the shadows of galaxies, would grow insatiable, consuming everything in their path. Planets, moons, and even entire star systems could be devoured, crushed into infinitesimal points of infinite density. Imagine Earth, our home, being drawn into the maw of a supermassive black hole, stretched and compressed into oblivion by the unimaginable forces at play. Even if planets somehow avoided these fates, the relentless compression of space-time would ultimately leave no corner of the universe untouched. The very fabric of reality would warp and twist, crushing matter into a singularity. In the final moments, the distinction between planets, stars, and even galaxies would vanish, as all matter converges into a single, unfathomable point of energy. This grim scenario forces us to confront the fragility of our place in the cosmos. Yet, it also highlights the incredible resilience of the universe's structures, which have endured for billions of years. The Big Crunch, while devastating, serves as a reminder of the impermanence of all things, even on the grandest scales. And as we ponder the fate of planets in such a universe, we're left with a profound appreciation for the delicate balance that allows life to flourish, at least for now. Now, let's turn our attention to neutrinos, those elusive, nearly massless particles that zip through the cosmos almost unnoticed. These ghostly travelers are everywhere, passing through stars, planets, and even us, rarely interacting with anything. But in the context of a big crunch, neutrinos might take on a far more active role than we'd expect. As the universe begins to collapse, the density of matter would increase dramatically, and neutrinos, despite their tiny mass, could start to have a noticeable effect. In a universe contracting toward a single point, the sheer number of neutrinos trillions passing through every square inch of space every second could become a significant factor. Their collective energy and momentum might influence how galaxies, stars, and even black holes behave as they're pulled closer together. But here's where it gets even more intriguing. Neutrinos are known for their ability to change flavors, oscillating between different types as they travel. During a big crunch, this behavior could become even more pronounced. The intense gravitational forces and extreme conditions might cause neutrinos to interact with each other or with other particles in ways we've never observed before. These interactions could potentially alter the balance of forces driving the collapse, either accelerating it or creating pockets of resistance that slow things down. And what about cosmic structures? Neutrinos, often thought of as mere background noise in the universe, might actually shape how matter clumps together as the universe contracts. Their subtle gravitational pull could cause galaxies to merge differently, or even create new patterns of density that ripple through space-time. In a way, neutrinos could act as cosmic sculptors, subtly guiding the final stages of the universe's collapse. Of course, all of this is speculative. Neutrinos are notoriously difficult to study, and we're still uncovering their secrets. But the idea that these nearly invisible particles could play a pivotal role in the fate of the universe is a fascinating one. It reminds us that even the smallest, most elusive pieces of the cosmic puzzle can have a profound impact on the grandest scales. So, as we ponder the big crunch, let's not forget the quiet influence of neutrinos. They may be small, but in the end, they could hold the key to understanding how the universe wraps up its story. As the universe contracts and hurtles toward a big crunch, the very fabric of reality begins to unravel, and with it, the delicate dance of chemistry that underpins everything we know. Atoms, molecules, and the bonds that hold them together would face a catastrophic breakdown, marking the end of chemistry as we understand it. But how exactly does this happen? Let's break it down. First, consider the extreme conditions that would arise as the universe collapses. Temperatures and pressures would skyrocket, creating an environment so chaotic that even the most stable chemical bonds would struggle to survive. Atoms, the building blocks of matter, would be crushed together with such force that their electrons, normally orbiting in predictable patterns, would be stripped away. This process, known as ionization, would leave behind a sea of subatomic particles, erasing the structure that allows chemistry to function. Chemical reactions, the very processes that give rise to life, would grind to a halt. Without stable atoms and molecules, there would be no way for elements to combine, no chance for the formation of compounds, and no possibility of sustaining the complex systems that make up stars, planets, or even the simplest forms of matter. The universe would devolve into a primordial soup of raw energy and particles, far removed from the intricate chemistry we see today. But it's not just the destruction of atoms and molecules that signals the end of chemistry. The fundamental forces of nature would also shift as the universe contracts. Gravity, already the dominant force in this scenario, would grow stronger, overwhelming the electromagnetic forces that hold atoms and molecules together. Without these forces, the rules of chemistry as we know them would no longer apply. The periodic table, the basis of all chemical understanding, would become meaningless in this new, chaotic state. And yet, even as chemistry fades, the universe would continue its inexorable collapse. The breakdown of chemical processes is just one step in the larger journey toward the big crunch. a journey that reshapes the very essence of reality. As we ponder this, it's worth asking, what would remain of the universe's identity once its chemistry is gone? The answer lies in the next phase of this cosmic unraveling. What happens to all the information that defines our universe if it were to collapse into a big crunch? This isn't just a philosophical question. It's a fundamental puzzle that ties into the very nature of reality. Information in physics isn't just data like the kind stored on your phone or computer. It's the fabric of existence itself, encoding the state of every particle, every interaction, and every moment in time. If the universe were to reverse its expansion and collapse, would all that information vanish, or could it somehow endure? In the late 20th century, physicist Stephen Hawking proposed a startling idea that black holes might destroy information. This became known as the information paradox, and it shook the foundations of physics. If black holes could erase information, what would that mean for a collapsing universe? The Big Crunch, in many ways, resembles a black hole on a cosmic scale, a gravitational collapse so extreme that even light can't escape. So, could the universe's information face a similar fate? Some theories suggest that information might not be lost forever. The principle of unitarity in quantum mechanics states that information cannot simply disappear. It must be conserved, even if it's scrambled beyond recognition. Think of it like tossing a deck of cards into the air. The order of the cards is lost, but the information, the identity of each card, is still there, just rearranged. In the same way, the information about the universe might be preserved, even if the universe itself collapses into a singularity. But here's where things get even more intriguing. Some physicists speculate that the Big Crunch might not be the end at all. Instead, it could be a transformation, a cosmic reset button. If information survives the collapse, it's possible that the universe could rebound in a new Big Bang, carrying forward the encoded history of its previous iteration. This idea, known as the cosmic bounce, suggests that the universe might be cyclical, with each cycle preserving the information from the one before it. It's a tantalizing thought. Our universe's story might not end with a crunch, but continue in an endless loop of creation and destruction. Of course, this is all theoretical. We don't yet have the tools or the understanding to say for certain what happens to information in a collapsing universe, but the question forces us to confront the limits of our knowledge and the mysterious nature of existence itself. What if the universe's history is etched into the fabric of reality, waiting to be rediscovered in a future cycle? Or what if, in the end, all that information is lost and the universe's story fades into oblivion? These possibilities remind us just how much we still have to learn about the cosmos, and how much wonder remains to be explored. What if the very fabric of the universe, its particles, stars, and galaxies remained mysteriously linked even as it collapsed into a big crunch? This is where quantum entanglement, one of the most puzzling and fascinating phenomena in physics, enters the picture. Imagine two particles separated by billions of light years, yet still influencing each other instantaneously. In a collapsing universe, where distances shrink and the cosmic stage grows smaller, entanglement could play a critical role in shaping the fate of everything we know. At its core, quantum entanglement is about connection. When two particles become entangled, their properties are intertwined, no matter how far apart they are. In an expanding universe, this connection might seem like a strange cosmic quirk, but in a universe collapsing toward a big crunch, the rules could change dramatically. As space contracts, those entangled particles would be brought closer together, potentially amplifying their interactions. What happens to these quantum links when the universe itself is squeezed into an ever-tightening cosmic ball? Could entanglement help preserve some form of order, or would it contribute to the chaos? One possibility is that entanglement might act like a cosmic glue, holding structures together even as the universe collapses. Galaxies, stars, and even the fundamental particles that make up matter could remain interconnected, resisting the pull of the crunch for a time. But there's a twist. As the universe shrinks, the energy density increases, and the rules of quantum mechanics might start to break down. The delicate balance of entanglement could be disrupted, leading to unpredictable outcomes. Would these quantum connections snap under the pressure, or would they somehow adapt to the extreme conditions? Another intriguing angle is how entanglement might influence the final moments of a collapsing universe. Some theories suggest that quantum effects could create a kind of quantum firewall, a barrier of entangled particles that prevents the universe from collapsing into a single point. Instead of a smooth, uniform crunch, the universe might end in a chaotic tangle of quantum interactions, with entanglement playing a starring role in its final act. Of course, all of this is speculative, but it highlights just how deeply quantum mechanics could shape the fate of the cosmos. Entanglement reminds us that even in the face of a big crunch, the universe is a place of deep, interconnected mysteries. As we ponder these ideas, we're left with a profound question. If the universe is capable of such intricate connections, what else might be possible in its final, fleeting moments? But what about time itself? Could something as fundamental as time come to an end during the Big Crunch? This isn't just a philosophical question, it's a scientific one. In a universe collapsing inward, the very fabric of spacetime could undergo radical changes. Some theories suggest that as the universe contracts, time might slow down, halt, or even reverse. Imagine a clock ticking slower and slower until it stops completely. That's the kind of scenario physicists are considering. Time, as we understand it, is tied to the expansion of the universe. The Big Bang set the stage for time to flow forward, but if the universe begins to collapse, the rules might change entirely. One compelling idea is that time could become cyclical, looping back on itself in an endless cycle of contraction and expansion. Or it might simply cease to exist altogether, leaving a universe frozen in a single eternal moment. What's fascinating is how these ideas challenge our understanding of existence itself. If time stops, does that mean all events, all possibilities, come to a standstill? Or could it open the door to a new kind of reality, one where time operates in ways we can't even begin to imagine? These questions push the boundaries of physics and philosophy, blurring the line between science and speculation, and here's where it gets even more intriguing. Some researchers propose that in the final moments of a collapsing universe, time might not just stop. It could transform into something entirely new. Picture time not as a straight line or a loop, but as a multidimensional structure branching out in ways that defy our current understanding. It's a concept that feels almost like science fiction, but it's rooted in the mathematics of spacetime. Of course, these ideas are still theoretical, but they invite us to think beyond the limits of what we know. If the Big Crunch were to happen, the end of time wouldn't just mean the end of the universe. It could mean the beginning of an entirely new way for reality to exist. And that's the kind of mystery that keeps scientists and all of us looking up at the stars, wondering what's truly possible. What would happen to consciousness if the universe itself began to reverse? It's a question that sits at the crossroads of science and philosophy, challenging us to think beyond the physical collapse of space and time. If the Big Crunch were to occur, bringing everything back to a single point, what would that mean for the very essence of awareness? Would consciousness simply vanish, or could it somehow persist, even in the face of such cosmic upheaval? From a scientific perspective, consciousness is deeply tied to the brain, a product of complex neural networks and the flow of information. But in a universe that's collapsing, those networks would eventually break down. Stars would dim, galaxies would merge, and the fundamental processes that allow for thought and perception would cease to exist. In this scenario, it's hard to imagine how consciousness could survive. It's like trying to keep a flame burning as the oxygen is sucked out of the room. Eventually, the fire goes out, but here's where things get intriguing. Some theories suggest that consciousness might not be entirely dependent on physical matter. For instance, certain interpretations of quantum mechanics propose that awareness could be a fundamental property of the universe itself, woven into the fabric of reality. If that's true, then even as the universe contracts, consciousness might not simply disappear. It could transform, becoming something entirely different, yet still present in some form. On the philosophical side, thinkers have long debated whether consciousness is an emergent property of the brain or something more universal. If it's the latter, then the fate of consciousness in a big crunch scenario becomes far more mysterious. Could it exist outside of time and space, untouched by the collapse of the cosmos? Or would it dissolve into the singularity, merging with the primordial state from which the universe first emerged? These questions don't have easy answers, but they invite us to explore the boundaries of what we know and what we might never fully understand. Whether consciousness would vanish or endure in a reversing universe, the very act of pondering its fate reminds us of how deeply intertwined we are with the cosmos. It's not just about the stars and galaxies, it's about the very essence of what makes us aware, alive, and human. And in that sense, the Big Crunch isn't just a scientific concept. It's a mirror reflecting the profound mysteries of existence itself. What if the universe doesn't end with a whimper or a fade, but instead collapses back on itself, only to explode into existence all over again? This idea, known as the Big Crunch leading to a new Big Bang, suggests that the cosmos might be stuck in an endless cycle of expansion and contraction. It's a fascinating concept, but how plausible is it? Let's break it down. Imagine the universe as a giant cosmic rubber band. Right now, it's stretching outward, galaxies moving farther apart as space itself expands. But what if one day that rubber band snaps back? This is the essence of the Big Crunch, a scenario where the universe stops expanding and begins collapsing under its own gravity. Everything, stars, planets, even time and space, would condense into an infinitely dense point, almost like rewinding the Big Bang. But here's the twist. Some scientists speculate that this collapse could trigger a new Big Bang, birthing a fresh universe from the ashes of the old one. This cyclical model of the universe isn't just science fiction. It's rooted in some of the most profound questions in physics. For instance, Einstein's theory of general relativity allows for the possibility of such a cycle, and certain interpretations of quantum mechanics even suggest that the conditions at the point of collapse could reset the cosmic clock. But while the math might hint at this possibility, the evidence is far from conclusive. One of the biggest challenges is dark energy, the mysterious force driving the universe's accelerated expansion. If dark energy continues to dominate, it could prevent the universe from collapsing altogether, making the Big Crunch unlikely. Still, the idea of a cyclical universe has its supporters. Some argue that it solves one of the most puzzling questions in cosmology. What came before the Big Bang? If the universe cycles endlessly, there's no need for a before, just an eternal loop of creation and destruction. It's a poetic notion, but one that raises its own set of questions. For example, would each new universe be identical to the last, or would it be different in some fundamental way? Could life, or even the laws of physics, change with each cycle? The implications are staggering. A cyclical universe would mean that everything we see, every star, every galaxy, every atom, might have existed countless times before in slightly different forms. It would also suggest that the cosmos has no true beginning or end, just an infinite series of rebirths. But without definitive evidence, this remains one of the most tantalizing what-ifs in science. What we do know is that the universe is full of surprises, and the story of its ultimate fate is far from written. Cosmic strings, these mysterious, thread-like structures woven into the fabric of space-time, are more than just a fascinating theoretical concept. If they exist, they could play a pivotal role in shaping the fate of our universe, especially in the context of a Big Crunch. Imagine the universe collapsing back in on itself, galaxies hurtling toward one another, and space-time itself folding in ways we can barely comprehend. Now, picture cosmic strings as cosmic threads pulling at the very fabric of this collapsing universe, potentially altering its structure and behavior in profound ways. So, what exactly are cosmic strings? They're hypothetical one-dimensional defects in space-time, thought to have formed during the early moments of the universe. Picture them as incredibly thin, incredibly dense filaments stretching across vast cosmic distances. If they exist, they'd carry immense energy and gravitational influence, capable of warping space-time around them. During a big crunch, as the universe contracts, these strings could become even more active, their gravitational pull intensifying as the space between them shrinks. One possibility is that cosmic strings could act as cosmic anchors, creating regions of space-time that resist the collapse more than others. Think of it like a sheet of fabric being pulled tight from all sides, but with threads woven into it that refuse to fully contract. These strings might lead to the formation of dense knots or even pockets of space-time that remain intact long after most of the universe has collapsed. These regions could become the seeds of a new universe, potentially giving rise to a cyclical model of cosmic rebirth. But cosmic strings could also introduce chaos into the collapse. Their immense gravitational pull might cause space-time to tear or fold in unexpected ways, creating irregularities in the collapse process. Instead of a smooth, uniform crunch, the universe might experience a more turbulent and fragmented collapse, with regions collapsing faster or slower depending on the influence of nearby strings. This could lead to a universe that doesn't just end in a single catastrophic event, but in a series of localized collapses, each influenced by the intricate web of cosmic strings. What's truly fascinating is how little we know about these hypothetical structures. While they're predicted by some theories, like certain models of string theory and early universe physics, we've yet to detect any direct evidence of their existence. Yet, their potential impact on a big crunch scenario is undeniable. If they're real, they could be the hidden architects of the universe's final moments, shaping the collapse in ways that challenge our current understanding of space, time, and gravity. As we ponder the role of cosmic strings in a big crunch, it's worth asking, could these enigmatic structures hold the key to understanding not just the end of our universe, but the birth of a new one? Their influence might extend beyond the collapse, offering clues about the cyclical nature of existence itself. And while we're still in the realm of theory, the possibility that cosmic strings could play such a pivotal role in the universe's fate is a reminder of just how much we have yet to discover about the cosmos. As the universe contracts toward the big crunch, the very fabric of reality as we know it begins to unravel, and at the heart of this unraveling are quantum fields. These fields, which underpin everything from the smallest particles to the forces that govern them, are the invisible framework of our universe. But in a collapsing cosmos, they wouldn't remain stable. Instead, they'd undergo profound transformations, potentially leading to the breakdown of the rules that define our existence. Quantum fields are like the stage on which the drama of particles plays out. They're everywhere, even in what we perceive as empty space, and they give rise to particles like electrons, quarks, and photons through fluctuations. But in a universe hurtling toward the big crunch, the stage itself starts to warp. The immense gravitational forces generated by the collapsing matter and energy would squeeze space-time to unimaginable densities, and this extreme environment would push quantum fields to their limits. What happens then? One possibility is that the fields would become unstable, losing the delicate balance that allows particles to exist. Imagine a symphony where the instruments suddenly go out of tune, no longer producing harmonious notes but chaotic noise. Similarly, quantum fields might no longer sustain the particles we rely on for the structure of matter. Electrons, protons, and neutrons could dissolve back into the underlying fields, leaving behind a sea of energy without form or function. Another scenario involves the fields themselves merging or transforming. In the intense heat and pressure of the Big Crunch, the distinctions between different quantum fields, like the electromagnetic field and the Higgs field, might blur. This could lead to a unification of forces, a moment where all the fundamental interactions we've spent centuries studying combine into one primal force. It's a concept that echoes the early moments of the Big Bang, but in reverse, as if the universe were rewinding its own creation story. But here's where things get even stranger. Quantum fields are governed by probabilities and uncertainties, principles that define the quantum world. In a collapsing universe, these principles might no longer apply. The very laws of quantum mechanics, which have been our guide to understanding the smallest scales of reality, could break down entirely. What replaces them? We can only speculate, but it's a reminder that the Big Crunch isn't just the end of stars and galaxies, it's the end of the rules that make the universe comprehensible to us. This brings us to a profound question. If quantum fields fail, what happens to information? In our current understanding, information is never lost, even in black holes. But in the chaos of the Big Crunch, even this fundamental principle might collapse. The universe could erase its own history, leaving no trace of the galaxies, planets, or life that once existed. It's a humbling thought, one that underscores just how fragile the foundations of reality might be in the face of such cosmic upheaval. As we peer into this speculative future, it's clear that the Big Crunch isn't just a physical event. It's a transformation of the very laws that define existence. Quantum fields, the bedrock of our universe, could be the first to go, taking with them the particles, forces, and information that make up everything we know. And in their absence, the universe might rewrite its own rules, leaving us to wonder what, if anything, would come next. As the universe inches toward a hypothetical Big Crunch, one of the most intriguing questions is how virtual particles, those fleeting bursts of energy that flicker in and out of existence, might behave under such extreme conditions. These particles, often described as the universe's quantum foam, are everywhere, even in the vacuum of space. They're not just theoretical curiosities, they're fundamental to how particles interact on the smallest scales. But as the cosmos contracts, their role could shift dramatically. Imagine the universe squeezing tighter and tighter, galaxies colliding, and space itself shrinking. In this scenario, the quantum vacuum, the so-called empty space where virtual particles arise, would become denser and more chaotic. Normally, these particles appear in pairs, borrowing energy from the vacuum and annihilating each other almost instantly. But in a contracting universe, the rules of quantum mechanics could start to warp. The energy borrowed by virtual particles might not be returned so easily, and their interactions could become unpredictable. This raises a fascinating possibility. As the universe collapses, virtual particles might not simply vanish as they usually do. Instead, they could accumulate, creating pockets of energy that could influence the fabric of spacetime itself. These accumulations might act like tiny seeds, triggering fluctuations that could either stabilize or destabilize the collapsing cosmos. For instance, if virtual particles clump together in certain regions, they could create localized distortions, potentially altering the rate at which space contracts or even forming new structures within the shrinking universe. But it's not just about the particles themselves. Their behavior could have cascading effects on larger cosmic structures. Stars, galaxies, and even black holes might feel the ripples of these quantum-scale changes. As the universe contracts, the interplay between virtual particles and massive objects could become a delicate dance, with each influencing the other in ways we can only begin to theorize. Of course, this is all speculative, as the Big Crunch remains a hypothesis. But pondering the fate of virtual particles in such a scenario opens a window into the strange and beautiful interplay between quantum mechanics and cosmology. It reminds us that even the tiniest phenomena could have profound implications for the universe's ultimate fate. And as we explore these ideas, we're not just learning about the cosmos. we're uncovering the intricate connections that bind everything from the smallest particles to the largest galaxies. What if wormholes, those mysterious tunnels through space-time, could play a role in the fate of the universe during a big crunch? These theoretical structures, often depicted in science fiction as shortcuts across the cosmos, might hold surprising significance if the universe were to reverse its expansion and collapse inward. But how would wormholes behave in such a scenario? Would they survive the crushing forces of a collapsing universe, or would they vanish entirely? Let's dive into the intriguing possibilities. Wormholes, also known as Einstein-Rosen bridges, are solutions to the equations of general relativity that suggest the existence of shortcuts connecting distant points in space and time. In a stable universe, they're already a tricky concept to grasp, requiring exotic matter with negative energy to keep them open and prevent them from collapsing. But in a universe undergoing a big crunch, where everything is contracting under the pull of gravity, the rules of the game change dramatically. The immense pressures and densities as the universe contracts could either destroy wormholes entirely or, paradoxically, create conditions where they might thrive. One possibility is that wormholes could become unstable and collapse as the universe contracts. The increasing density of matter and energy might overwhelm the delicate balance needed to keep a wormhole open, causing it to pinch off and disappear. This would mean that any hope of using wormholes as escape routes or time-saving shortcuts would vanish along with them. But there's another, more intriguing idea. What if the extreme conditions of a big crunch actually make it easier for wormholes to form? In a universe where space and time are being compressed, the fabric of reality itself might twist and fold in ways that naturally create these cosmic tunnels. Imagine the universe as a piece of fabric being squeezed from all sides. As it contracts, the folds and wrinkles in that fabric could create pathways, wormholes, that connect distant regions. These wormholes might not last long, but for a brief moment they could offer a glimpse into a collapsing cosmos, linking places that were once impossibly far apart. And if wormholes did form during a big crunch, could they potentially offer a way to escape the crushing fate of the universe? It's a tantalizing thought, though one that remains firmly in the realm of speculation. Of course, wormholes are still theoretical, and their behavior in a collapsing universe is even more uncertain. But exploring these ideas helps us stretch our understanding of space, time, and the ultimate fate of the cosmos. Whether they collapse, persist, or even multiply during a big crunch, wormholes remind us that the universe is full of mysteries waiting to be unraveled. And as we continue to ponder these cosmic enigmas, we're reminded just how much there is left to discover about the nature of reality itself. As the universe hurtles toward a big crunch, a hypothetical collapse where everything contracts back into an infinitely dense point, our understanding of the fundamental forces that govern reality could be turned on its head. Picture this: gravity, electromagnetism, and the strong and weak nuclear forces, the very framework holding our universe together, might undergo dramatic changes as the cosmos shrinks. But what does that mean for matter, for energy, and for the very fabric of existence itself? Let's start with gravity, the force we're most familiar with. In a collapsing universe, gravity would become the dominant player, pulling everything inward with increasing intensity. But here's where things get strange. As the universe contracts, the density of matter skyrockets and gravity's influence grows exponentially stronger. This could lead to a scenario where gravity overwhelms the other forces, reshaping the rules of physics as we know them. Stars and galaxies, once held in delicate balance, would be crushed together, their structures obliterated under the weight of this immense pull. Then there's electromagnetism, the force responsible for holding atoms together and enabling light to travel through space. In a big crunch, electromagnetic interactions could become distorted. As the universe contracts, the wavelengths of light would compress, shifting the entire electromagnetic spectrum. Colors we've never seen before might emerge, and the very nature of light could change in ways we can barely comprehend. Imagine a universe where the rules of electromagnetism no longer apply as they do today, where the bonds between atoms weaken or break entirely, dismantling matter at its core. The strong nuclear force, which binds protons and neutrons within atomic nuclei, might also face a crisis. In a collapsing universe, the immense pressure and density could cause protons and neutrons to merge, forming a sea of quarks and gluons, a state of matter known as quark-gluon plasma. This would effectively erase the structure of atoms, leaving behind a chaotic soup of fundamental particles. Similarly, the weak nuclear force, responsible for radioactive decay, could become unpredictable, altering the stability of matter in ways that defy our current understanding. If these forces are altered or overpowered, the consequences for matter would be catastrophic. Atoms, the building blocks of everything we know, could disintegrate. The familiar forms of matter, solids, liquids, gases might cease to exist, replaced by exotic states of energy and particles. The collapse of the universe wouldn't just mean the end of stars and planets. It could mean the unraveling of the very laws that make existence possible. Yet, even as we explore these grim possibilities, there's an awe-inspiring beauty in imagining how the universe might rewrite its own rules. The Big Crunch isn't just an end. It's a transformation, a moment where the fundamental forces could reveal new dimensions of reality we've never glimpsed before. And while the thought of such a collapse might seem unsettling, it reminds us of the delicate balance that holds our universe together, a balance that, for now, allows us to explore, to wonder, and to exist. What happens to the building blocks of reality itself when the universe begins to collapse? Quantum information, the fundamental data that describes the state of every particle and the relationships between them, holds the key to understanding how the universe operates at its most basic level. But in a scenario where everything is hurtling toward a big crunch, the fate of this quantum information becomes one of the most fascinating and perplexing questions in physics. Could it survive the collapse, or would it be lost forever, erased as spacetime itself folds in on itself? To grasp this, let's start with what quantum information actually is. Unlike the kind of information we're familiar with, like the data on your phone or the words in a book, quantum information is far more abstract. It's the intricate web of probabilities that define the behavior of particles, from their position and momentum to their spin and entanglement with other particles. This information isn't just stored, it's constantly evolving, shaping the reality we observe. But in a collapsing universe where spacetime is shrinking and the fabric of reality is being compressed, what happens to this delicate web? One possibility is that quantum information could be preserved, somehow encoded into the very structure of the collapsing universe. Think of it like a cosmic backup system where the data is compressed into smaller and smaller spaces but remains intact. Some theories suggest that as particles are squeezed closer together, their quantum states might become entangled in new and complex ways, creating a kind of ultra-dense quantum archive. This would mean that even as the universe contracts, the information that defines it could still exist, albeit in a radically different form. But there's another side to this coin. The extreme conditions of a big crunch, hence gravitational forces, unfathomable temperatures, and the breakdown of spacetime itself, could destroy quantum information entirely. In this scenario, the delicate balance of probabilities that govern particles might be disrupted beyond repair, leading to a total loss of coherence. It's like trying to read a book that's been set on fire. The information might still be there, but it's scrambled beyond recognition. If this happens, the universe wouldn't just end. It would end without a trace of its former self, leaving no record of what once was. And then there's the most intriguing possibility, transformation. Instead of being preserved or destroyed, quantum information might evolve into something entirely new during the Big Crunch. Imagine a sculptor taking a block of marble and chiseling it into an entirely different shape. In the same way, the collapse of the universe could reshape quantum information, creating new patterns and relationships that we can scarcely imagine. This idea ties into theories about cyclic universes, where the Big Crunch isn't the end but the beginning of a new cosmic cycle. In this view, quantum information isn't lost, it's reborn, carrying the echoes of the old universe into the next. The fate of quantum information isn't just a theoretical puzzle, it's a question that challenges our understanding of reality itself. If the universe collapses, will the story of its existence be erased, rewritten, or carried forward into a new chapter? The answer lies at the intersection of quantum mechanics, cosmology, and some of the deepest mysteries of physics. And as we continue to explore these ideas, we're reminded of how much there still is to learn about the universe, and how much we have yet to discover. Picture this, a universe collapsing in on itself, galaxies crashing together, and all matter being pulled into a single, infinitely dense point. But what if something strange, something almost unimaginable, could influence this process? Enter exotic matter. Unlike the ordinary matter we see every day, exotic matter doesn't play by the same rules. It's the wild card of the cosmos, with properties that seem to defy the laws of physics as we know them. And in the context of a big crunch, this mysterious substance could be the key to understanding how the universe might meet its end. Exotic matter is theorized to have negative energy or negative mass, meaning it could repel rather than attract. Imagine a cosmic tug of war where ordinary matter is pulling everything inward, while exotic matter is pushing outward. This bizarre behavior could drastically alter the dynamics of a collapsing universe. Instead of a straightforward collapse, the interplay between these two types of matter might create a chaotic, unpredictable finale. Could exotic matter slow down the collapse? Could it even prevent the universe from reaching that infinitely dense point? These are the questions that keep physicists up at night. To put it in simpler terms, think of exotic matter as a cosmic brake pedal. If the universe is hurtling toward a big crunch, this strange substance might act as a counterforce, potentially delaying or even reshaping the collapse. Some theories suggest that exotic matter could create pockets of stability within the collapsing universe, regions where the laws of physics behave differently. These pockets might not follow the same rules as the rest of the cosmos, leading to a fragmented and uneven collapse. But here's where it gets even more intriguing. Exotic matter isn't just a theoretical curiosity. It's already connected to real-world phenomena like wormholes and dark energy. Wormholes, hypothetical tunnels through space-time, require exotic matter to remain stable. Dark energy, the mysterious force driving the universe's accelerated expansion, shares some similarities with exotic matter's repulsive properties. Could these connections hint at a deeper cosmic pattern? If so, exotic matter might not just influence a big crunch. It could be a fundamental piece of the puzzle in understanding the universe's ultimate fate. Of course, all of this is still in the realm of theory. Exotic matter has never been directly observed, and its existence is inferred from the mathematical frameworks of advanced physics. But if it does exist, its role in a big crunch scenario could be nothing short of revolutionary. It challenges our understanding of gravity, energy, and the very fabric of space-time. And while we may not have all the answers yet, exploring these possibilities reminds us just how strange and wondrous the universe truly is. As we peer into the possibilities of the Big Crunch, one of the most mind-bending aspects to consider is the fate of space-time itself, the very fabric that underpins our universe. Space-time, as Einstein revealed, isn't just a static stage where cosmic events play out. It's a dynamic, flexible structure that bends and warps under the influence of matter and energy. But what happens to this intricate geometry when the universe begins to collapse? Imagine the universe as a vast, stretching sheet of rubber. Right now, it's expanding, pulled taut by the forces of dark energy and cosmic expansion. But in a big crunch scenario, that sheet starts to contract. the distances between galaxies shrink and the curvature of space-time becomes more pronounced. At first, this might seem like a simple reversal of the Big Bang, but the reality is far more complex. As the universe contracts, space-time wouldn't just revert to its original state, it would undergo extreme distortions. The closer everything gets, the more intense the gravitational forces become, warping space-time in ways we can barely comprehend. Stars, galaxies, and even black holes would be drawn closer together, their immense gravitational fields creating ripples and folds in the fabric of reality. Over time, these distortions could grow so severe that space-time itself begins to break down. One possibility is that the very dimensions we take for granted, length, width, height, and even time, could start to collapse. Time, which flows steadily in our everyday lives, might become erratic, speeding up or slowing down as the universe contracts. In the final moments of the Big Crunch, space-time could become so twisted that the laws of physics as we know them cease to function. Reality, as we understand it, would unravel, but what does this mean for us? Well, if space-time geometry is the foundation of existence, its collapse would redefine everything, from the way matter interacts to the very nature of causality. Events that once followed a clear cause and effect relationship might no longer make sense. The universe, in its final moments, could become a chaotic, unpredictable realm where the rules no longer apply. This isn't just a theoretical exercise. It's a profound exploration of how deeply interconnected space, time, and matter truly are. The Big Crunch wouldn't just mark the end of the universe. It would rewrite the rules of reality itself, forcing us to confront the limits of our understanding and the fragility of the cosmos we call home. But beyond the equations and cosmic timelines, the Big Crunch isn't just a scientific theory. It's a mirror reflecting some of the most profound questions humans have ever asked. What does it mean for our existence if the universe itself could one day collapse? If everything we know, galaxies, stars, planets, life, could eventually fold back into a single point, does that change how we see our place in the cosmos? These aren't just questions for physicists. They're questions for philosophers, poets, and anyone who's ever looked up at the night sky and wondered why we're here. The Big Crunch forces us to confront the idea of impermanence on a cosmic scale. If the universe has a finite lifespan with a beginning, middle, and end, what does that say about time itself? Is it a linear march toward an inevitable conclusion, or is it cyclical, with the possibility of rebirth hidden within the collapse? Some philosophers have argued that the cyclical nature of the Big Crunch could suggest a kind of cosmic renewal, a universe that collapses only to expand again, endlessly repeating itself. But others see it as a reminder of the fragility of existence, a humbling thought that everything we build, create, or dream could one day be undone. This leads us to another layer of the discussion: purpose. If the universe is destined to collapse, does that mean our actions, our achievements, even our memories are ultimately meaningless? Or does the fleeting nature of existence make every moment, every act of kindness, every discovery even more precious? It's a question that's haunted thinkers for centuries, from ancient Stoics to modern existentialists. The Big Crunch doesn't provide answers, but it invites us to grapple with these ideas in a new light. It challenges us to find meaning not in permanence, but in the here and now, a call to live fully, even in the face of an uncertain cosmic future. And then there's the nature of reality itself. If the universe can collapse, does that mean reality is something we can define, or is it more fluid, more mysterious than we realize? Some theories suggest that the Big Crunch could be a reset button, erasing the current universe to make way for something entirely new. Others propose that the collapse might not be the end, but a transition into a different kind of existence altogether. These ideas blur the line between science and philosophy, pushing us to rethink what we mean by real and whether reality itself is as fixed as we assume. Ultimately, the Big Crunch isn't just a story about the universe, it's a story about us. It's a reminder that we're part of something vast and ever-changing, and that our understanding of existence is still evolving. Whether you see the Big Crunch as a cosmic ending, a new beginning, or simply a thought experiment, it invites us to reflect on what it means to be alive in a universe that's constantly rewriting its own rules. And maybe, in that reflection, we find not just answers, but new questions to carry with us under the stars. The Big Crunch isn't just a concept tucked away in the pages of astrophysics textbooks. It's a profound glimpse into what could be the ultimate destiny of everything we know. Picture this: galaxies spiraling closer together, stars collapsing into darkness, and the fabric of space-time itself folding inward. It's a cosmic reset button where the universe might not just end, but begin anew. This idea forces us to confront questions that stretch far beyond science. What does it mean for existence itself? How does time unravel in the face of such a cataclysmic event? As we've explored, the Big Crunch isn't just about collapse, it's about transformation. It challenges us to rethink our place in the cosmos and consider the possibility that endings might be gateways to new beginnings. Whether or not this theory becomes reality, it's a reminder that the universe is a place of infinite mystery, where even the most fundamental laws of physics can bend and reshape under the weight of unimaginable forces. So, as we wrap up this journey through the stars, let's take a moment to reflect. What does the Big Crunch mean to you? Is it a terrifying end, a hopeful renewal, or simply a fascinating idea to ponder? The universe is full of stories waiting to be told, and this is just one of them. Share your thoughts in the comments below. We'd love to hear your perspective. And if you're hungry for more cosmic explorations, hit that subscribe button and join us as we continue to uncover the wonders of the cosmos. Until next time, keep